and X, Y, Z are strings over sigma. So it's different to have an element of the alphabet than to have string over the alphabet. A string is a sequence of finite length. So the length of string is the number of elements of the string. So for example, and normally you use this symbol here, like the cardinality symbol is used to use the length of the string. So for example, the length of A, B, is 5. Special attention to epsilon, which I forgot to mention. There is the empty sequence is called epsilon. The epsilon is like the sequence with no elements. The empty sequence. And the size of the length of that sequence is, of course, 0. We're going to write this symbol, a to the n, to denote the string that results from having n a's. So, for example, a to the 1 is a, but a to the 5 will be a. Okay? And you can define recursively this operation like this. A to the 0 is defined as epsilon, and a to the n plus 1 is simply a to the n followed by a. Is that clear? Juan, Esteban?
Profe, ¿podemos hablar en español o...?
No, the problem is that the course is in English, right?
Ok.
So
Igualmente ustedes sí pueden participar en español, ¿no?
Sí, esa era como la duda.
Sí, sí, pueden.
Ok, Juan Fernando, sí, pues obviamente, o sea, la clase es en inglés, pero se me olvidó aclarar que ustedes pueden hablar en español o en inglés, como quieran. Lo mismo que en los exámenes, los pueden escribir en inglés o los pueden escribir en español. Pero Juan, ¿estás entendiendo lo otro?
Sí, señor.
Ah, bueno, me alegra. Okay, so going back to this point, let's say, Juan Esteban, can you explain this definition of a to the n to see if everybody got it? Juan Esteban, are you there? Okay, he's not. Juan Floyd?
Sí, profe, aquí estoy. ¿Me escucha?
Can you explain this definition?
Pues, profe, lo que tengo entendido es que cuando uno hace a la 0, vacío. Segundo que ese es el vacío. Cuando uno hace a la n más 1, es a la n por a.
Followed by a, seguido de a. It's not a multiplication, it's a concatenation.
Ah, pues, sí, concatenación, pues, porque estamos hablando de strings.
Okay. Another important operation is the star operation. If sigma is the alphabet, sigma star is the set of all sequences over sigma, all of them. So, for example, the star of AB or the set AB it has got all these elements: epsilon, A, BA, B, all the sequences that you can, all the strings that you can write with A and B. So one question: what will be the cardinality of this set? Joan? Or somebody wants to say it? Santiago?
Should it be infinite?
Yes. Very good. So another question: is there a set of strings whose start operation gives you a finite set? Like
The empty set?
Empty set.
very good, the empty set. So the start of the empty set, the size of this will be 0. But there is another one. There is another one. Any ideas? Okay, so let's see. So look at this. The start operation over sigma over the empty set is defined as having one string only, which is the empty string. Okay. Okay. Something important about sets and strings is that, as you might remember, the order doesn't matter in a set, right? AB is the same as BA, but in strings, AB is different from BA. Also, multiplicity doesn't matter in sets. So AB is the same as AB, but A followed by A followed by B is different from AB. Okay, so these are basic operations. Then you have concatenations of strings, and concatenation is associative, of course. X concatenated with Y concatenated with Z is the same as X concatenated with YZ. And what is this telling me?
Que la cardinalidad de dos elementos concatenados es igual a la suma de la cardinalidad de los dos elementos por separado.
That is correct. So this is gonna be a homework for you all, homework. As you remember, we mark all the homeworks with HW. Show this. Try to see if you can show this. Okay? You know what the sum is, and you know what the cardinality of a string, the length of the string is. So you should be able to prove this. Okay? I give you an idea. If you reason by induction, you will have X concatenated with the epsilon is the same as X, and X concatenated with epsilon will be X plus. But you know that the size of this is 0. Then you get this equation. And then try to reason by induction. Okay, what other things you need to know? Okay, so just as you have this A to the N when A is a symbol of the alphabet, you have the same operation. You extend the operation over strings. So X to the N is the string that results from having N copies of X concatenated one after the other. So for example, AAB to the 5 is AB concatenated with AB, AAB, AAB, AAB 5 times. and is defined the same way, right? X to the 0 is epsilon, and x to the n plus 1 is the string x to the n concatenated with x. Okay, so another notation that we're going to use is this one. If you have a symbol a and string x over an alphabet sigma, then you write a number ax or hash ax to denote the number of a's in x. So for example, the number of ones in 0, 0, 0, 0, 0 is 0 because there is no 1 in that string. But the number of zeros in this string, that you can count them, is 8. So another notion that you need to know is the notion of prefix of a string. The prefix string x is the initial substring of x, is an initial substring of x. So the way to define this formally, you have any questions? Sorry. So for example, AAB is a prefix of the string A, B, C, A. Okay, because it appears in the beginning, right? And the dual notion is the notion of suffix. A suffix is the final string of a no string. So the string, for example, BCA is a suffix of AABCA because it appears here. How do you define this formally? Let's see, you can do it. So we write definition, say y is a prefix of x if, what will you write here? Any ideas? Santiago?
I would say that it's if x is a suffix of y.
No, and that is not true. For example, here you see AAB. AAB is a prefix of AABCA, but AABCA is not a suffix of AAB. So when do you say, when will you, how will you define that y, a string y, is a prefix of x? Formally, using logic and mathematics. What you saw in my...
Y is subset of X.
But why are you using subsets? A string is not a set, okay? String is a sequence of symbols. A set is a collection of symbols. There are two different things, remember? Very different. And so different that you actually make, you see, AB is the same as BA, a set, but not a string. So there are two different things. Okay.
I've got a question.
Yeah.
Why don't you include C in the prefix of on the right side, the example, the letters C, A, A, B, C? Why not?
Okay, the prefix is not unique, so there could be many prefixes. Actually, there could be, if the sequence is of size n, of length n, there are n plus 1 prefixes. So yes, A, B, C is also a prefix of this string because you have it here. So what are all the prefixes of this thing?
The subsequence?
Yeah, all the prefixes are one is the empty string, right? Trivially, because that's one. The other one is A. The other one is AA. The other one is AAB. The other one is AA. The one you said ABC, and the other one is AABCA. So the sequence is of size 5, length 5, and we have 1, 2, 3, 4, 5, 6. So n plus 1 prefixes. All of these prefixes are except all these prefixes, but the last one are called proper prefixes because this one is proper because it's like kind of included, but it's not the whole string. These two, these two, these two, these two, except this one because this one is the sequence itself. Okay. It's the same when you talk about proper subset, or similar when you say proper subset or subset of a set. A proper subset of a set is a set that is included. Okay, a proper A is a proper subset of B if A is included in B and A is different from B. It's the same here. A prefix is proper if it's a prefix and is different from the string. Okay, so I have several questions there, Santiago.
Yeah, should we be using instead the definition that you just told us, the x power of 0 equals epsilon and x to the power of n plus 1 equals x to the power of n x? Should we be using that instead to make the definition of y is a prefix of x?
Let's try it. What did you exactly suggest here? So you say y is a prefix of x if what? Tell me, I just write down what you say.
If we're able to demonstrate the definition of operations, which is right a little bit upper from what you said, which was that x to the power of n plus 1 is the same as x to the power of n x times x. Sorry.
X n plus 1 is the same as what?
X n times x, which is the definition, right?
Yeah, but this is actually always true. I mean, x to the n plus 1 is always the same as x to the n followed by x, because that's actually the definition of concatenation of this operation, sorry. Well, what we want here, probably it's not clear enough, is how do I capture this definition of prefix? I think you all understand what prefix is, right? Do you understand the notion of prefix? So what I want you to do is to try to define it mathematically, precisely. Like when you try to specify an algorithm, what it does, you should be able to use mathematics to specify that properly. Joan?
Yeah, I have a question of the prefix. I mean, so you said if the prefix is the string itself, is it not a prefix, or what do you say?
Oh, no, proper. We're gonna see that proper here. A prefix y is a proper prefix of x if y is not different from the empty string and y is different, sorry, if y is not the empty string and y is not x. So, okay.
And about the definition, can we say something like, is there a way to like enumerate the elements? Like I can say something like
Yes, you
if
can say
y0 is equal to x0, like that.
you can say, for example, if I don't know, you can say if y is 1 to the n and x is what? I mean, yes, you can use this kind of notations, but I don't know how you're gonna use it for the definition. Do you have an idea?
Yeah, I was thinking like if y0 is equal to x0 and y1 is equal to x1, and do it like that until y is over.
Yeah,
I,
that
I don't know how to exactly put it in
yeah,
pretty terms, but that's my idea.
I'm gonna try to polish your definition to get it to a very concise definition, but your idea works. And that's how you work in mathematics and in software engineering too. You start with an idea and you start to polish it, an algorithm, and you start to polish it. Okay, let's try that. So you say if x is of the form x1, sorry, let's say x1, x2 till xn, and y is of the form y1, y2, yn, and what you want to say is that xy is equal to yi for all I till n, and also n, sorry, I made a mistake here, I need m here, and m is, I guess this is what you want to say, right, Joan?
But it should be on the for all I with m, not n.
Ah, yeah, sorry, that was the mistake I had made before. Yeah. Mm-hmm.
Yeah, it's exactly that. Thanks.
Yeah, so that would work, but it's like it can be improved a lot. So let's compare this definition to say if there exists set in the alphabet, so you say sigma star, such that y is equal to y. So this is the same. So y is a prefix of x. If you can find a set such that y is equal, sorry, x is equal to y followed by z. Do you understand that definition? Jeremías?
Not quite.
Are you saying like, isn't that like saying that every string can be a combination of a prefix and a suffix?
Yeah, that's true. But I'm saying y is a prefix. I'll read it in another way to see it more clear. Y is a prefix of x if x can be written as y followed by something else. That's something else I call it z. Is it more clear now? For example, in this case, in the first example, uh, and we have A, B, C, A. So this is Y, and this is X. Okay, and check if this is the case. If there are set such that X is equal to Y, Z, is that true? Which
Yes.
one would be the set?
CA?
Exactly, CA. So is that clear now, Jeremias?
Yes, it's more clear.
Yeah. So this definition is equivalent to the one that Johan gave us, but it's like more compact. So he uses less notation. So one would normally prefer this one. But this one probably offers you more detail. If you like that, you can choose the other one. Okay, so then we'll use lots of operations of set, which I'm not going to define because you're supposed to know what's union, intersection, complement. You can read it in the book if you have forgotten. Okay, we move to set concatenation, which that one you might not know. A set, not string. A set A concatenated with B is the set of all strings X concatenated with Y, such that X is in the first set, that is A, and Y is in the second set, B. So here is a question. Can somebody calculate that concatenation?
I mean, like it's up there in
Yeah,
yellow.
it's up there.
In yellow.
Then if it's up there, can you explain it?
Well, we are like making every possible combination of the strings.
Not
Like
quite.
this distributive property?
Not exactly. It's like the first one, like the first element of the first one. We concatenate with each of the other two of the other one, and do the same with the next
Like this
element of the first set.
distributive.
Yeah, that.
Exactly. So it's not the same as having all possible combinations. It's, you take the first string from the first set and the second from the second set. Okay, and you think that AB is the same as BA? If you took all combinations, that would be the case. So is AB concatenated with BA the same, and why not?
No, it's not.
No.
So it's different.
And why, Santiago?
Because if we start using distribution to do the same operation, we'll get different results since the first element will be BA instead of AB.
Exactly. And you remember this operation from your course, right? In functional programming. This is the Cartesian product. Sorry, this one. Remember what the Cartesian product of AB times BA would be? Do you remember or you forgot? Okay, the Cartesian product takes all pairs, right? So one pair would be A and B, another will be ABA. So do not get confused. A Cartesian product will not have strings as elements. You will have pairs. Here, concatenation is actually strings, okay? Uh, And then, of course, you use the notation again for the same. You say a to the n is simply the set a concatenated n times with itself. So a to the 0 is the string, the set that have the empty string only, and a to the n plus 1 is a concatenated with a to the n. Okay? So, for example, this is what you obtain by AB with AAB to the square is simply all these combinations, okay? Which was the one that we saw before. And finally, this operation, the asteroid of A star, is how we'll explain it here. One way to define it is to say that A star is A to the 0 union A to the 1, A to the 2, A to the 3. That is the infinite union of all A to the n. Okay. So basically, let's see. What would you think that means that AB, for example, AAB to the star will have all these strings. This, all this. Okay. Another way to define A star is to say that is the set of all sequences of this form, x1, x2, xn. Each one of these is a string. And what you require is that every xi is an element of A. In other words, A to the star is the all possible combinations of the string, concatenations of the string of a set with themselves. Okay, that's it. What other operation could be interesting? This is something that you should keep in mind. Set concatenation distributes over unions. That is, A distributes over A concatenated with B union C is the same as A concatenated with B union A concatenated with C. But this is not the case for the intersection. Okay. It is not the case that A concatenated with B intersected with C is the same as A concatenated with B intersected with A concatenated with C. If you want to try, there is a counterexample here. Take A equals to AAB, B equals to this set, and C equals to the set with the empty string. And try to compute this one, and you will see that they are not the same. In fact, try this as a simple exercise. Homework, verify this. Let's take this. Okay, so this way, and you need to read this chapter we just saw. we just saw some notation that we're gonna be using from now on during the whole course. Okay. Now we're gonna give some intuition about final state automata. In the next class, we're actually gonna define them properly. But final automata are, you might be familiar with them because they are very simple structures. You have sets. Let's say in this case, we have two sets. And then we have transitions between the sets. So you can say, for example, with a symbol 1, I move from this state. I give it a name, S, and this is called T. So I move from S to T if I read a 1. And I stay in S if I read a 0. So with 0, with 0, with 0 I stay there. With 1 I move here. Okay. Some of the states might be initial, and some of them are accepting states or final states. That means that if you get to the final state, the machine might stop there. So the start states, they have this notation. That means that this state is a starting state or start state. And the terminal or accepting states are denoted with this, like a double circle. That was an ugly double circle. I'll try it again. That's a little bit better. And then, of course, you might have transitions even after this one. For example, you have with 1, and again with 0, you have a transition like this. I suppose you already have seen this in one way or another, right? Have you, Juan?
Yeah, but not with the final state represented like that.
Okay.
We've seen this in Moore and Mealy state machines.
Yeah.
So this is basically the structure of it's a graph. So final state automata is a graph where the nodes are called states and the edges are called transitions. And the idea is that this machine is reading strings, symbol by symbol, and they move from one state to another according to the symbol they are reading. For example, if my input string is 0, 1, 1, the transition could be then this one. I start here. So then at this point, it reads a 0, then it does this. It stays in S. Then reads the 1, and then at this point, you make the transition to T. And then you read another 1. That means that you read this one and move to S. So you are back to this initial state. Okay. Do you understand that? How to move in the automaton according to the input that you're reading, right, Santiago?
Yes, my question is, which is like the definition of the different states? Like, what's the purpose of state S and state T? What's the difference between one another?
Yeah, very good. So the start state is to define when you where in which state you begin the computation. So you always start with the initial state from here in this case. And the final or accepting state is used for the definition of acceptance. You're gonna say that a machine, a final state automaton, let's say call it M. This is M. You say that M accepts X, or X, let's say, if you can read X from left. This is all intuitive. We're going to define this properly. From left to right, and end up in a final state. I forgot to say here, you can read X from left to right, starting from the initial state and end up in a final state. So string is accepted. You can read it from left to right totally, starting from the initial state, and when you finish reading this, you will finish in a final state. In this case, for example, this string will not be accepted. Why? Because if you start reading from the initial state, you will start with 0, 1, 1, and you will end up in the state S, which is not an accepting or terminal state. Is that understood? Is that clear? Juan? Juan Floyd?
¿Me puede repetir, profe? Por favor.
Well, I don't know exactly what to repeat. The question or whether this is a set?
No, ninguna pregunta, profe.
No entendí lo que dijiste.
Yo dije algo.
No entiendo cuál es. Bueno, Jeremías, do you understand why 011 is not accepted by M?
Yes, and I've got a question. Is that like after executing an algorithm, there are like certain states, and if the algorithm ends in a state that is not the final state, can we say that it is not correct or something like that? Is that a use of that or?
Yeah, it's similar, but it's not the notion of correct. It's the notion of not accepting. But yes, another way to see this, if you want to think of the graph theory, is the following. Remember, this M can be seen as a graph, right? You can see it's a graph. These are the nodes. There is a special node to begin with and some terminal nodes. String is accepted by the automaton or graph M if there is a path that begins in S and ends in T, and that path is exactly this one. Okay, so let's see, is there, for example here, is there a path in this graph 0, 1, 1 that start here and ends up here? No, right? Because the only path 0, 1, 1 that you will find is this one. 1, 0, 1. That's the only path 0, 1, 1, and that path that does not end up in T. So some question. I think Juan Fernando have a question.
If you add 1 or if you write a 0 instead of the last one, then M upsets the X, or?
That's a good question. So let's start with is this string accepted by M?
No, it shouldn't, right?
No, with a 1 instead of that 0.
Okay, yeah. Very good. Will this string be accepted?
Yeah.
Yeah, exactly. So why? Because in that graph, there is a path from S to T labeled exactly as 0, 1, 1, 1. Okay. That's one way to define it. Another way to define it is like you move according to the states and you end up in a final state, starting from the initial state. Santiago?
Yes, and my question is, if we have three different states, which would be considered the final state?
You can choose them.
Oh, it's completely arbitrary. We could
Yeah.
choose either the second or the third to be the final state, and that could be also accepted.
Yeah, you can have this situation, for example. You have three states. You have let's change it a little bit with 0 and 1. And there are like two distinguished kind of states. One is the starting state, is one, and this is the final state. And this is just a regular state. It's not starting, it's not accepting. And if you want, it could be also be accepting. You can have two accepting states. What you can have, at least in this, the first kind of automata that we want to see, you cannot have an automaton with several initial states. There should be only one initial state, but there could be many accepting states. Very, very good question. We're gonna see later on some automata called non-deterministic automata, and in that case you can have multiple initial states. Okay. Okay, going back to this one. Okay, Joan has a question and Jeremias has another one, I think. So Joan.
Are there any, like, is it possible to have an operation that is not defined? For example, let's say that the last, for example, the starting state didn't have the 0 coming back to it, like, and we have this string that starts with 0. Is that okay?
Yes, yeah, that's an ugly answer, but actually, I mean, you could say yes and no. But when you don't write that transition, it's because you are assuming that the transition doesn't lead you to an acceptance. I'll explain what you mean. For example, let's suppose that I think what John wants to say is that, can I have this? So from the state S, I define what happens when I read a 1, you say I move here, but I am not specifying what I do with a 0. Sometimes you might do that, but basically there is something implicit about this. You should always say what happens to every symbol that you're reading, but if you don't do it, it's because you are basically assuming that you have the situation. If I don't write it, you're going to imagine that you have this. So basically, it's like if you don't define what happens with the symbol like 0 here, what you are saying implicitly is that you're going to a sync state. Why is it called a sync? Because you move to this state, and this state, if you read 1 or 0, you stay in the same state. So you are like in a sync. You are stuck there. Okay? That's what you're saying. So another way to look into this is that you always have like a total function, meaning that the transition is defined for all possible symbols. So it must be always a total function. If you don't specify this, because you are assuming that this function is mapping that element, in this case the 0, always to some special kind of state whose transitions are always a loop. So you see, from this point, you're stuck. You will never get to an accepting state. In that way, whenever I don't write a state, a transition for a state. Sorry, a transition for a symbol. What I'm saying is I'm going into this kind of states. I don't know if that's clear, John. Is that clear?
Yeah, I get it.
So basically, you don't define it because you are saying you read that symbol, you get stuck, and you're never gonna go to an acceptance state.
It's kind of like an error, like that shouldn't happen, maybe.
Yeah, exactly, something like that, like a default transition into a sync state. Santiago? I'm sorry, Jeremias.
Yeah. So we can say that there are infinite possible sequences that are accepted by M, right? Like for reaching the final state.
Yes.
So when we write for example, we need to write the sequence. We should always write the shortest sequence or
No.
any sequence.
Any sequence. That
All right.
that is gonna give you. That's a good question, Jeremias. What we're gonna define next, or not define, we'll define in the next class. Right now, I'm only giving you intuitions. I prefer to give intuitions first before the definitions. What we want to do is now to define the language of automaton M. So the language of M is the set, and it's going to be the language of any machine. The language is always the set of all strings that are accepted by M, and only those. Okay? So for example, as Jeremias just pointed out, there are infinitely many strings that are accepted by this language, by this automaton. One is 0111, another one is 111, another one is 5 ones, and so on. So that will be the language of M. So the language of M is written like L of M is equal to all X such that M accepts X. Okay? That's the language. And I want you to think about what would be, there is a way to, there are infinitely many strings that M accepts, but they have a common feature. Can you identify it? Can you see it?
The amount of ones is odd.
Excellent. Exactly. So the language of M is the set of that M in particular is the set of all binary strings having an odd number of ones. Very good, Hermias. So, and then you can see that that set is infinite, yet it can be described succinctly, like with this automaton and with the definition that you just said. So, and we're gonna say that a language is regular if you can write down or draw, if you wish, an automaton that whose language is that set. Okay. So a set, let's say A is called regular if there exists an automaton M such that the language of M is A. So, for example, the set of all binary strings having an odd number of ones is regular. Why? There is your automaton. Now, also the set of all having an even number of ones is regular. How you prove that? Well, not like this because that one doesn't. But maybe you can find an automaton, maybe modifying this one that accepts strings Those is all strings that whose number of ones is even. How do you do that? Any suggestions? Oh, before going to that, Santiago, you have a question?
Yes, I wanted just to clarify, continue with Joan's idea that there is a state that goes directly from S that is inside a loop. Is it possible that that loop is considered an acceptance?
Yes, yes, you can have, you can, I mean, this sync, I mean, definitely you can write that if you want. Let's go on to this one, 1, 0. And then you say that this is acceptance state. Yes, you can have that automaton, definitely. It will accept, it doesn't accept all strings, does it? No. For example, it doesn't accept the string 1, 1, right? Because
Yes, it
one,
will be back at the beginning.
so with 1, 1, it will move here, and then here, and then stays in S. To accept the string, you have to read it all completely, okay? So 1, 1 is still not accepted by the string, but 1, 1, 0 is accepted, okay? Because 1, 1, 0. And then 1, 1, 0, and 1, or any, after this 0 accepts anything, okay?
Okay, thank you.
You're welcome. So now I want to prove that the set of binary strings having an even number of ones is regular. For that, you will have to find an automaton that accepts that set. Can you do it? Can you imagine how? What will you change there?
Teacher, there has to be a connection from the final state to the start state.
No.
That's like obligatory.
Oh, sorry. Yes, in order to accept at least one string, there must be at least one path from the initial state to the final state. That's for sure.
And from the final to the initial.
Yeah, but the state can be final and initial at the same time. There is no restriction about that. Okay. In this case, no. The initial state is different from the start state, but you can have an automaton where the initial state is also an accepting state. In particular, we will accept the empty string. I could have this, for example. Now the empty string will be accepted because it's when you start. Okay, but then can you tell me what yeah, Hermes?
I don't know like the general rule, but maybe if you add one node at the upper edge and one node at the lower edge, like in the same flow of things, that would be an even number of ones.
So do you want me to add transitions from where to where, or states?
From S to another state in the middle of S and T.
To regular states, I think he's trying to say.
Like this?
Yeah, and both edges, the new edges with ones, like to go to the next state.
Okay, I got it. So what you want is this, right?
Exactly that, and the same on the lower part.
And on 0 like this?
Yes, that's
Okay. That's a good idea.
But we will need to make the start state also acceptance, right?
That's more what that was exactly what I was thinking. Okay, let's try this one to see. Okay, 2 ones are accepted, but 4 ones are not accepted. Let me just see.
Oh, it should be like every even number, not just some, right? Of
Yeah,
ones.
exactly. The language of all strings with an even number of ones.
So yeah, with what Johan said, like the starting also
Yeah,
will be a final.
but then try to think about this. Let's simplify that then. Do you see now why it works?
Yes, that's better.
You just need to change the state. So, and also, since 0 can be considered even, so it's good because it accepts the empty string. The empty string has 0 numbers of ones, and if you consider 0 to be even, then it's okay. Okay, so that said will also be regular because we just found a new automaton M that whose language is actually the set of all strings having an even number of ones. Okay, so these are basically what we have seen in this class is all the notions that are important for this course, which is sets, concatenations, and so on and so forth. And I gave you some intuition about what a final state automaton is. And in the next class, we're going to define this properly. Okay. And we use some basic examples of two automata, recognizing two sets, the set of even of strings with an even number of ones and with an odd number of ones. You might imagine that you can do the same with zeros, like an even number of zeros and an odd number of zeros. And we're going to see a lot of examples, useful examples in computation. And we're going to also see what you cannot do with this automata. In other words, we're going to find sets that are not regular. That means that it's not possible to find an automaton M whose language is that set. And the set of sets that are not regular are very important in computation because they are, let's say, a little bit more complex. Okay, so let's stop there. Any questions? No questions. Nicole, it was clear.
Yo, profe.
Wait,
Ok, sorry.
Nicole.
Yes, teacher, it was clear.
Okay. Juan Fernando, tell me.
Pues te la voy a hacer en español porque no sé bien cómo indicarte rápido en inglés. Era para ver si me podía volver a explicar la parte que está abajo a la izquierda del language of M. Que esa parte no me quedó clara, lo que explicaste ahí.
The language of M is the set of all strings that are accepted by the automaton. So in this case, is this so every sequence sorry, every sequence with a number with an even number of ones will be accepted. So that will be the language of that automaton M. Okay?
Okay, thank you.
Okay, if there are no more questions, anyway, you can
I
stay.
have a question.
Yeah, John.
What does the ST mean? That abbreviation?
ST.
It's below.
Ah,
That
sorry.
20.
Sorry, in English that means such that.
Okay, thanks.
Such that. Tal que. Okay. Okay, good question. And if there are no more questions, I leave you with Nicolas. He will answer further questions or give you more intuitions if you want. If there was something that you didn't understand, and feel free to ask Nicolas. So he will be here for the rest of the class, okay?
Okay.
I'm gonna switch to Spanish. Acuérdense que todas las preguntas las pueden hacer por Teams en el chat. Nicolás va a dejar el material de hoy para que miren las tareas que tienen que hacer y el video también queda allí. Bueno, no siendo más, nos vemos en la próxima clase, muchachos. Hasta luego.
Profe, qué pena. ¿Este archivo lo vas a subir ahorita?
Nicolás sube los archivos.
Vale. Pues para
En
hacer
5
las
minuticos lo
homework.
subo.
Yes. Vale,
Profe,
gracias.
las tareas las vas a... ¿Cómo vas a la revisión de las tareas o cómo te las presentamos?
Nicolás, al comienzo de la clase, en los primeros 15 minutos, revista las tareas, el que los haya hecho o le quiere hacer una pregunta, se las presenta a él, porque él va a llevar las tareas, recuerden que forman parte de la participación, entonces él es el que lleva la cuenta de esa parte. ¿Listo, Juan?
Listo, profe. Gracias.
Nada, hasta luego, muchachos, que estén muy bien.
Adiós.
Hasta luego, profe.
Hasta luego, profe.
Gracias,
Muchísimas
profe.
gracias. Feliz resto de día.
Muchachos, pues voy a quitar la grabación ya.